All right, we're back. We've laid the foundation, and now we're ready to get into statistical hypothesis testing or statistical significance testing. You might also hear it called null hypothesis significance testing, test of significance, all sorts of names thrown around out there. And as we begin this journey through this part of the course, I want to bring you to a table that we're going to start creating. As we encounter a test, we are going to talk about when it's appropriate. When I was working at the University of North Texas in a research lab and doc students would come in, they would have a tremendous amount of detailed knowledge about different parts of statistics and research. But what I found was missing was the big picture. So if they had dissertation data, the question to me was always, what analysis do I use? And so what I want to do is, as we go through these analyses, I want you to be aware of not just how it works, and how to interpret it, but when is it appropriate? Okay? So the first test we're going to use is called the Z-test. Now, I will go ahead and tell you that in real life, we don't use this test a lot, but because it's the most basic form of significance testing, we use it to lay the foundation so that you can understand the more sophisticated analyses. Another thing I want to encourage you on is once you get this process down, it's going to be repeated quite a bit. So once you understand how a Z-test works, and then we have about 3 different types of t-tests that we'll look at, but the process is the same on all of them. Now, what's different is when is it appropriate? It's a little bit different in the interpretation as far as kind of that qualitative piece of the interpretation. It's different in the point and click part of SPSS, but the heart of it is the same. Okay, so we want to use a Z-test when we have one sample and we want to compare our sample to the population. But here's another particular thing about the Z-test. The population mean and standard deviation are known. Okay? So again, in real life, knowing the population mean and standard deviation is it's pretty, I don't want to say pretty rare, but it's just something we don't encounter a lot in education research anyway. But the way I want to talk to you about the Z-test is through an example. So I'm going to click over to my PowerPoint here. I think going through the process in a context is going to be more meaningful. So here we go. We are going to use this example about Dr. Meyer. Now, Dr. Meyer is interested in the increased number of homeschooled students in the United States. In his state, 4th grade students have a mean score of 250, standard deviation of 50 on a test of achievement. All right, so think about our table a minute ago. A Z-test is going to work for this because we know the population mean and the population standard deviation, and here it is noted. Remember how we talked about a couple of lessons ago that when you have a population mean, it's not X bar anymore, it's mu. And then the population standard deviation is 50. So we have the sigma symbol, not the standard deviation as it is incorrectly noted here. Okay. Now, what he's going to do is take a sample of 25 homeschooled 4th graders, administer the test, and calculate the mean of the scores. Because he wants to know, are the homeschooled 4th graders scoring the same as just your typically educated, more traditional, I guess I'll say, like in the classroom type students, not homeschool students, okay? So he wants to know if, say, public school students or general fourth grade students have this mean and this standard deviation, how are homeschool students going to compare? And he's specifically going to make that comparison using a sample of 25 and administering that same achievement test to his 25 fourth graders and compare and see, hey, how are these homeschooled fourth graders doing in comparison to the population? Okay? So, step one, we're going to formulate the question as a statement or as a hypothesis. So, the mean of the population of achievement scores for homeschooled fourth graders, in fact, is equal to 250. That is, the homeschooled mean is also 250. All right? So what he's saying is homeschooled kids are not performing better than, I'm just going to refer to them as public school kids. So homeschool kids are the same as public school kids. Okay? That is what he is proposing. All right? So, the way it's worded, and you're going to love this kind of null hypothesis significance testing wordiness. It becomes very awkward, so just bear with me. But if his hypothesis were true, and remember, his hypothesis says homeschooled fourth graders are the same in terms of achievement as public school fourth graders, okay? So if that hypothesis were true, what sample means would be expected by chance alone? That is due to sampling variation if an infinite number of samples of size 25 were randomly selected from this population. Well, we can figure that out, okay? Because we know that a sampling distribution of means is really a probability distribution for a particular sample size, and so we can figure out what we need to know. All right, so here, this is our standard error, right? So we already know the mean, and if we plug what we know into the formula, we know our standard error becomes 10. We're going to need this information in a minute. All right, so step 3. So he's ready to go. He selects a single random sample from the population of homeschooled fourth graders, size 25, and administers the test. He then computes the mean for his sample. All right. Now, I'm going to go through step 4 and step 5, and then we'll actually calculate it and see. So in step 4, he compares his sample mean with that of all possible sample means, determines where his sample mean would fall in comparison to all other possible sample means. So in other words, he's going to look at his sample mean on a sampling distribution of means. Based on where his sample mean falls, he can accept or retain his hypothesis. Okay, so let me back up to this step. So remember, back when we did the coin flips, right? Remember that? Let's see if I can get there's my pen. Remember the coin flips. And when we did the coin flips, we ended up, where'd you go? Pen, not cooperating. Okay, there you are, pen. All right, when we did our coin flips, remember how we ended up with that curve? And we had, all right, this possibility of 0, this possibility of 1, this possibility of 2, this possibility of 3, and this possibility of 4 heads. Remember when we did that and we had that distribution? It's the same idea here. So what he's going to do is take a look at that theoretical sampling distribution, because unlike our coin flips that we could actually do, he cannot randomly sample a size of 25 an infinite number of times. But we know these are theoretical and they're out there. So there is a distribution for sample size 25. Remember, there's a distribution for every sample size a theoretical distribution, because, right, we can't do it, but if we could randomly sample for infinity, we would end up with a nice normal distribution, right? So when he gets his mean, he is going to see, okay, well, where does my mean fall in comparison to all, these are all the possibilities, right? Just like our landing on heads possibilities, we plotted all those possibilities. It's the same thing here. All the possible means are plotted here, theoretically anyway. So we're going to see, where'd my n go? We're going to see how his sample of 25 and his mean compares with all the possibilities. Is his mean way out here? Or is it way out here? Or is it somewhere in the middle? Right? Because remember what we know about a sampling distribution. The mean of a sampling distribution, so the mean of the means, is actually the what? It's the population mean. So if the population mean is actually right here, because we know that because the mean of the means of a sampling distribution is actually the population mean. That's a mouthful. Well, where does his sample fall in comparison to the actual population mean? Okay, so this is the process we're going through. So based on where his mean falls, is it over here? Is it close to the population mean? Is it over here? Wherever it falls, he's going to either accept or retain his hypothesis, or he's not. He might reject it. And remember, his hypothesis says homeschooled fourth graders also have a mean of 250. Okay, so based on where it falls, he's either going to agree with himself or disagree with himself. Okay, so let's look at this. Here are a couple of possibilities, and this is sort of what I was drawing before. Let's think about A. All right, so he draws his sample of 25, calculates the mean, and what if his result ends up right there on A? What if it ends up right here? So based on what we know about this nice curve, what do we know about those probabilities way out here? They get, as we go this direction into the tail and this direction, what happens to the probability? It gets smaller, right? So whatever this probability is going to be small because it's in the tail. All right? What if his sample mean falls here? What do we know about that probability? All right? What probability is right here in the middle? Do you remember? Oh, that's a terrible line. I'm sorry. What probability is right here in the middle? Remember 50%? 0.5? Well, this is pretty close to 0.5. So maybe like 0.46 or 0.45, something like that. Well, 0.45 compared to something really tiny over here, this might be like 0.023. So if you think about probability in terms of percentages, 2.3% compared to 45%. And so we're thinking and asking ourselves, what's the probability he would have gotten sample mean B if his hypothesis is true is 45%. What's the probability he would have gotten sample mean A if his hypothesis is true, which says this? It's really small. Okay, and that's when we're going to get into this indirect proof. Okay, so sample mean A. Assuming the hypothesis to be exactly true, it is not very likely, remember we said it's that really low probability, that Dr. Meyer would have obtained sample mean A strictly by chance alone. Therefore, it may be possible for Dr. Meyer to conclude that the mean of the fourth grade homeschooled sample is different from 250. All right, so let me go back up here and talk you through this again. All right. right? So let's just assume that that's where, let me get my pen back. One day I'm going to have a computer that works better than this one. Okay, so let's assume that his sample mean was right there. Okay, so, and let me just back up and say, remember, his hypothesis says the homeschooled mean is the same as the general population mean, which is 250. So this is a picture of all the possibilities under this condition, okay? So the probability he would have gotten the sample mean he got, if the hypothesis is true, is really tiny. It is 2.3%. So the probability he would have pulled a sample of 25, given them an achievement test, and got this mean is really small. Therefore, we're going to conclude that the hypothesis is probably not true. I'm going to have to stop right there for a second.